in the series of Dalgarno lectures. So probably many of you have been at the first 2 lectures already, and maybe some of you have already heard someone introduce Tilman, so I will be short. One thing that comes to mind when you look at CV is that one thing is true: physics makes you go around the world. It's actually something that a physics professor told us in one of the first lectures, and I said, yeah, sure, I'm solving these P sets all the time. I will go around the world for sure. It's actually true, and in Tilman's case, it's very very true, not only during your studies, but then also as a research scientist in Constance. You went to Paris twice, actually, with working in the group of Condensate. And then, as you already had secured, as I learned, the full professorship in Stuttgart, you did the best thing one should do in such a situation. Go away for a year, come to MIT, work with Wolfgang on quantum atom optics, and just enjoy the time before starting the full professorship. So these were all very fruitful visits, especially for the people who were visited. Condensate got the Nobel Prize, Wolfgang got the Nobel Prize. It's pretty good. Yeah? He's a good predictor. Then in Stuttgart, you found an institute on quantum optics, and the big breakthrough of dipolar quantum gases. So Tilman was the first, far before people really went into this field. He said, I want to condense chromium, and it was bloody difficult, but he managed to do it, and realize dipolar quantum gases for the first time. And now this is actually, as you know, a big field with lots of different species being pursued, and people learn from Tilman how to actually do it. So we're actually very happy to have him here for 3 months now in the CUA as a visitor. So I hope to pick his brain as much as I can in the following month. Today, though, we'll not talk about the dysprosium, chromium work that we have heard about on Thursday, but about Rydbergs and how they interact with Bose-Einstein condensates. So these funny animals will be important. So we're looking forward to a wonderful talk tonight.
Thank you, Martin, for this introduction, and thank you all for being here again. You know, if you give 3 lectures, it's a little dangerous. You know, it could be that in the final lecture nobody shows up anymore. It's boring. So I highly appreciate that you all came back and you want to listen to this final talk in the series about cold Rydberg atoms. So we will talk about animals like this and how we behave in a quantum gas. So this is about Rydberg atoms, and I'm just introducing Rydberg atoms on a very basic level. Think back to your initial atomic physics lecture. This is what is Rydberg, gave the name to this. Rydberg atom is actually pretty simple. Yeah? It has a positive core, maybe a rubidium plus ion, and an electron that is orbiting around this core at a large distance. And if you take one number home today, then it's just the size of these objects. Here I plot the wave function squared, so the electron density in the radial direction, for different Rydberg states, and the way you characterize Rydberg states is by their principal quantum number. Here is a principal quantum number of 100. This is the n, which is called the principal quantum number. And what you should remember now is a rule of thumb, namely that the size, the radius of this atom is about 1 micrometer if n is 100. Okay? And it scales with n squared. So if you go to 200, then the radius is 4 micrometers. So that's the kind of object that we are going to deal with. An atom, the diameter of which is 8 micrometers. So just to compare to other things that you know, a BEC, for example, can be smaller than this. So if you excite a Rydberg atom in a BEC, then you can think about the situation that the core is sitting somewhere inside this BEC, BEC and the electron is outside. It's possible. It's for the size of these functions. Now, in this talk, we will slowly add complexity by taking our Rydberg electron, and that is the single charge that we are going to talk about, which is then interacting with the condensate, and we will put first one atom, and then we are talking about a binding mechanism between this Rydberg electron and this ground state atom, that is a dimer, so it's molecular physics. We can put another one, then we have a trimer. We can put more, then we have maybe polymers. That is sort of two and few body physics. That's sort of the one part of my subtitle. And eventually you can put many or even a whole condensate inside. And then you talk about the many body physics aspect of an electron, a single charge, interacting with the collective modes of such a quantum tensor. That will be the end of it. So this many body physics, of course, is relevant in condensed matter physics, because if you think about a single charge interacting with collective motion of particles, what comes to mind is electron-phonon coupling. That's exactly what we also are going to see in this BEC experiment. Okay, so the outline for the seminar is a little bit about the history, actually, very briefly at the beginning, about the interaction of electrons with atoms and how these ideas about these Rydberg molecules actually came about. Then how do single Rydberg electrons interact in the BEC. We will have a little bit of chemistry, inelastic and also elastic interactions. And I will probably not have time to talk about the other charge, the heavy charge, the ion that is left behind. That eventually could also be important and interact with the condensate. So let's start with some history. And I'm always asking young members in the audience whether they recognize some people on this picture. So I'm talking about younger guys. So Fermi I already heard, that's great, yeah, so that's this guy, he won the Nobel Prize. There's another Nobel Prize winner on this picture. Is anybody know? Segre, yeah? The youngest in the audience. So this is Emilio Segre, and this picture was taken 1933 or 4 in Rome, where all these guys who partially at least Fermi, for example, later on went to the US, were still working on Rydberg physics. This is the so-called group of Rome, and they did spectroscopy, precision spectroscopy on Rydberg atoms. This is their precision measurement apparatus at the time. When you wanted to do a high precision spectroscopy experiment, you better bought a high dispersion prism. That's this prism, you get it from this company here. It's sort of Toptica. It still exists, by the way, and it's still selling some glass-based equipment, scientific equipment. And then you basically put your source on one end, like in this case it's a discharge lamp, where you have Rydberg atoms, yeah, they fluoresce. And you take this fluorescence through this prism on a photographic plate. Okay, and then you look at it. So here is a photographic plate with a Rydberg series. And you publish this, of course. Yeah, at that time, you also publish in Nature, of course. The important stuff is in Nature here, Amaldi and Segre, 1934. There's a longer version with this title. It's an Italian title, but you can guess what it means. It's about the effect, effetto, yeah, della pressione, so that's the pressure, yeah, so it's a pressure shift on the elevated terms, which are the Rydberg levels, yeah, in alkali atoms. That's all I can say about Italian. That's what I read from this title here. So they measure pressure shifts, and they measure the pressure shift on the Rydberg series. So what they do is they basically take 2 of those Rydberg spectra at different background gas pressures. So this is a sodium spectrum, so they put a sodium discharge lamp and they fill it with some buffer gas, in this case hydrogen, first at some low density and then at some high density. So these are very high densities in our field, but they can do this all the way up to ambient pressures. And then they observe what happens to these Rydberg levels. I assume this for you here. So what you see for this particular level here, you see the whole series here, but for this level, you see that the line is actually shifted. There's a pressure shift, and there's a broadening. This line is broader than the other one. Okay. Now, what they did this systematically for different densities. So here's the density, here's the shift in delta, and they did it for different alkalis, potassium and sodium, and for different buffer gases. Okay. So here you see the hydrogen data, and you see that the shift scales linear with density, and that's okay, that's what you would expect. And you see that it does not depend on whether it's a potassium or a sodium. So basically, it's really the electron that counts, that is on this Rydberg orbit. This positive charge that is left behind isn't really important. So both data points, all these data points fall in one line. Then you measure the slope of these curves, and you see that for some gases, in this case, for hydrogen, there's a positive shift. So this is a blue shift. For other gases, that's this little r here, there is a negative shift, so it's a red shift. Other gases had zero shift. And this was basically totally unexpected at the time. Especially the blue shift. Because you would say, okay, this ground state atoms is maybe a polarizable medium. Yeah, you have an electric field that holds the electron in the Coulomb field of the ion. If you put a polarizable medium, all that can happen is that the energy gets lower. That's sort of the classical expectation. But in many cases, just the opposite was observed, namely a blue shift. And that required the input of a clever theorist, namely Enrico Fermi in that case, who then came up in the same year with a paper to explain this effect as a quantum mechanical scattering effect. So what did Fermi do? He takes this electron and the polarizable atom, I already put uridium, that's our case, but it could be hydrogen too or any of those buffer gases. And the potential between those is just given by a 1 over R4 law, basically, that contains the polarizability here. Yeah? So there's an electric field around the charge that falls off like 1 over R squared. The potential is given by the dipole moment that is induced by this electric field, so it's alpha E times E, so it's alpha E squared. So the overall potential is 1 over R4. So then this electron basically interacts with this polarizable atom via this potential, and the question is how to describe this correctly. He has then realized that basically the length scale of this scattering given by the de Broglie wavelengths of the electron is much larger than the range of interaction, and therefore you have to treat this as a quantum mechanical scattering effect. Which means if your wavelength, if your electron wave comes here, and you would have a node here at the origin of the coordinate system, due to the presence of this scatterer, then the origin of the scattered wave function is actually shifted a little bit. This is, by the way, an original figure from his paper in 1934. And that explains immediately what is the meaning of the scattering length, namely the shift of the origin of the scattering wave function. Okay. So, although there are some wiggles here due to the short-range physics, the overall effect asymptotically is just the shift, and that is described by this scattering length. And then he said, well, okay, I can effectively describe the asymptotic behavior by a pseudopotential, which in its simplest form, actually already Fermi realized, of course, that this is not the simplest form here. The real pseudopotential has to have an d over dr term here. We talked about this already, but the simplest form, if you have a homogeneous system, is this form. And then you can replace this potential by this, and then think about S-wave scattering only. And the only quantity that you then need to know is the scattering wave. what is the scattering length? Well, it's the most probable value is the range of interaction. Okay, how do you calculate the range of interaction? You just equate the kinetic energy and this potential energy, so 1 over characteristic distance squared equals 1 over characteristic distance to the 4th power. You resolve it, you get an effective range, which is just the square root of reduced mass mu times the polarizability. That's 18 Borel. Okay. So for rubidium, that's 18 Borel. And that's more or less the scattering length that rubidium has, however with a negative sign. Okay, so then the question is, the buffer gas basically affects the electron and gives rise to this shift. That is the explanation for the data that was measured by Amaldi and Segre. This line now basically tells you essentially the value of the scattering length. And this scattering length can be now either positive or negative, or 0. So with this explanation, that this is a quantum mechanical scattering effect, Fermi resolved this puzzle and sort of interpreted these density shift measurements as scattering length measurements for the electron ground state scattering that happens here when the electron is far away from the positive charge. Good. Then the next question was, I mean, you have now we have understood the effect on the spectrum, so on the electron, but you can reverse this question and ask what is the effect on the ground state atom, because this poor ground state atom now sits in the electron orbital, and it could also be affected, of course, by this scattering. Yeah. This was of course not so relevant at that time because they didn't have cold atoms, but as we have cold atoms now, you can ask this question, and of course it was answered, where is Hussein? Here, by Hussein and Chris Green in this famous paper 2000, namely they just take the same equation, and that's of course a very, very simplified version of what they write in the paper. It's much more elaborate in reality, but you just take the same equation that we just had, like here. You say the density shift is given by scattering length like the density of the buffer gas, so you turn it around and you say the energy shift of the atom is scattering length times the density of the electron. Okay, that's what they write here. This is the electron density. Okay. So what is the electron density? Well, we know it. It's just the square of the Rydberg wave function. So if I now take this Rydberg wave function of an S-state, multiply it with a negative scattering length, I get this green potential here, I quantize it, and I get the binding energies for these Rydberg molecules. This is the paper. You can also have much more fancy structures at the moment when this electron interacts, let's say, in a resonant way. We will come back to that, or with a degenerate manifold of levels, which is shown here, giving rise to this famous trial-by picture. We have seen those molecules in 2009 for the first time. That's actually a pretty simple experiment. You take a dense gas, such that the probability that you find the ground state atom inside the orbital is finite, and you just do 2-photon spectroscopy. So you take a red photon and a blue photon, you scan the frequency, and you count how many Rydberg atoms you excite. Okay, so here is a spectrum, this is a frequency, this is the ion count. You see there's an atomic line, that is sort of the 0. And then on the red side, because we are talking about bound states, so at lower energy, you find some lines. Yes? And actually it's not only a single line, there are actually several lines, because there are several bound states. They can all be nicely calculated, and the theoretical understanding of these positions is very good at the moment. But if you scan further, then you actually see that this same structure appears again, just at twice the frequency. And the way we interpret this is that we say, okay, now there is not only one ground state atom inside the orbital, but there are two of them inside. And the way they interact with the electron is via such a short distance that there is no indirect mutual additional interaction between those ground state atoms. So the effect on the binding energy is just additive. And if you have some phase in this, then you can say, okay, maybe there's even a tetramer. So that is already a 6 years old discovery that you can not only have dimers, but also 3 trimers and so on. Now let's play with this a little bit. Of course, we can play with a principal quantum number, and we can play with a density. So if I just now give you the numbers for about 10 to the 12 atoms per cubic centimeter, that's, let's say, a thermal cloud, and a principal quantum number of 40, then you would have 1 or even less than 1 atoms inside, and you would have maybe weak dimer lines. But if you now increase the principal quantum number, of course you make the volume of this Rydberg orbital bigger, it's this n squared law, and you will end up with about 4 atoms inside, already at this low density of 10 to the 12. So if you think about it, the overall interaction effect is independent of n, because you are increasing with the principal quantum number the volume. Therefore, you dilute the electron, so the electron density goes down, of course, with n to the -6, but the number of ground state atoms inside the orbital grows, of course, with the same volume, so it grows with n to the 6. So you would expect, as you increase the principal quantum number, that the average shift on your Rydberg line stays constant. So, and that's what you can basically see here. Well, here you see first the binding energy of a dimer for different principal quantum numbers, and you see this n to the 6 power law that I was just describing. So if you go up with the principal quantum number with the logarithmic scale, you start with binding energies of a few 10 megahertz, and you end up with binding energy of 100 kilohertz. Okay, here is the spectrum at 71. You see this is 1 megahertz here, about 1 megahertz width here that we scan. And in this 1 megahertz you find the dimer, the trimer, the tetramer, and maybe even the pentamer. Okay. So you can measure those frequencies and check, of course, that they have all this n to the power 6 scaling law. And of course you can even go further up in the principal quantum number, but what happens then is these lines just move so close together that you can't resolve them anymore. So the only thing that is left in this situation is a shift and a broadening, just like Amaldi-Segret, 1934. It's the same thing. Okay, now let's look at our apparatus. Some people have asked me about details. I just promised to show a picture. This is our PEC apparatus, the next generation, where we have a magnetic transport into a glass cell. In this glass cell, you see, first of all, there's a lens inside, so we have good optical access with high numerical aperture, such that we can focus a laser beam into the center of our condensate. You see also a channeltron detector and an MCP detector here. The atoms actually are magnetically transported along here, and then we just take a 90-degree turn and move them into the central cube, and this cube is actually a Faraday cage which is protected by wires. So it's hand-woven wire mesh that students, manually make in our lab. Okay, and all of this sits in one of these Japanese glass cells that I have seen in some labs here as well. Okay, so this will allow us take a condensate and basically excite a volume inside this condensate that is, let's say, 1 micrometer in diameter. And that is much smaller than the blockade radius. I assume you have heard a lot about Rydberg blockade. The only point in this talk where we make use of this blockade is to ensure that there's only a single atom. This volume, this excitation volume is so small, and once there is one excitation, there will be no further excitation. Okay, so that way we can be sure we study a single electron or a single Rydberg atom inside the condensate. Okay, so let's look at the spectrum again. This is a low density spectrum with this dimer, trimer, and tetramer peaks here. And you already see this is at 62, yeah, that there is some substructure, and we have some experts here, you see here, who is calculating line shapes in thermal gases and BECs, because you can consider this to be an impurity that has some subsequent main body dynamics that gives rise and that reflects in the line shape essentially. So here is the thermal gas, this time at about 10 to the 13 atoms per cubic centimeter. And now the question is, how does it look like in higher densities? Now, if you talk about higher densities, it essentially means that these ground state atoms come closer and closer to the inner part, to the basically origin of the coordinate system is where the positive ion is sitting. The electron moves in the Coulomb potentials from its classical turning point, which is actually here, gains energy. You see that the de Broglie wavelengths gets shorter and shorter. And at some point, it has an energy, in the particular case of rubidium, but it's similar in all alkali atoms, where it can not only scatter via S-wave, but it can experience a P-wave shape resonance. So what is this? P-wave shape resonance means that you are not only scattering through S-wave, but you also can scatter through a higher partial wave. Yeah? And these are two scattering partners that are clearly distinguishable. So it's an electron in the ground state atom, so you can have S-wave, P-wave, E-wave, and so on. Nothing is forbidden by symmetry. So the next partial wave is the P-wave. It has a centrifugal barrier, and for the ground state atom, basically, there can be a bound state sitting behind this barrier. It turns out in rubidium this is the case at 23 millielectron volts. So whenever the electron comes back from its classical turning point, it has 23 millielectron volts, then it will hit this bound state here and it will experience a resonance scattering. What is the effect on the potential? These potentials can be calculated here, for example. You see that instead of just having this S-wave potential, which is this green line, you at a certain distance, which is this resonant distance now, see that the potential goes crazy. It experiences a divergence here. And that, of course, is very important if you go to high densities. If the ground state atoms happen to sit here, they will experience this part of the potential. And if you want to understand your line shapes, it's very important to understand exactly this resonant physics very well. Here I show you the same thing blown up. I mean, here this is 10 megahertz. This is 200 megahertz. So the green potential is almost invisible. It's more or less flat. The S-wave is not very important, but you see that this P-wave resonance scattering here induces a divergence that is substantial. Yeah? It goes to very, very large energies. Eventually, it even connects to the next higher lying Rydberg manifolds, or the next lower lying Rydberg manifold. Okay. So this needs to be taken into account when we now look at the spectrum in a Bose-Einstein condensate. Okay. And here is such a spectrum. This is a 40S, and now, of course, this is much higher density, a few times 10 to the 14. So we are not scanning only 2 megahertz here, or 1 megahertz, but we are scanning 100 megahertz. Okay. So rule of thumb is always 10 to the 12 is 100 kilohertz. So if you see 50 megahertz or so, then this is 5 times 10 to the 14 as a density. Okay. And now the question is, okay, we see molecular lines. This is a 40S, so binding energies are like 15 megahertz or 12 megahertz or something. So this is the dimer, trimer, tetramer. But on this side, of course, we are losing the resolution because all these polymer lines, if you want to speak in this language, sort of start to overlap, and you basically just have a long tail in your spectrum. And the question is, how can we understand this tail? And for this, we make a little model. This is, of course, a very simplified model. We say, let's throw particles into this potential that are immobile. So we just do the experiment so fast that nothing is allowed to move. And we just take, let's say, a Poissonian distribution of particles as in the condensate, no correlations. And these green and blue balls are just such ground state atoms. And if this ground state atom happens, if it sits here, it contributes minus 15 megahertz to the shift. And eventually what you are going to see for a specific configuration is the sum of all these contributions. So the sum of all these shifts gives you the resonance frequency of excitation for this particular configuration. And now you see that there are particles sitting in the vicinity of this resonance, and that those guys contribute a lot and are especially important if you want to understand the tail of the spectrum reaching out to very large red frequencies. And this can be seen here. If we now take this simplified model here, which has a lot of assumptions, not only that the particles don't move, but also that everything is just additive, such that basically the electron is not altered by the presence of these ground state atoms, which is, especially around this resonance, actually not really true. But still, if you do this kind of model, you can explain this tail here at high frequencies very nicely. Yeah? Whereas the S-wave treatment alone, this is the dashed line, would not predict any signal at minus 100 megahertz. This model, including this P-wave shape resonance, explains that we do see a finite signal here, and it even explains more or less the line shape of this wing. Of course, as this is not quantized, I mean, we just throw in classical particles, it cannot explain the discrete nature of these molecular lines on this side here. But I think one can clearly say that with this kind of data, we start to see the effects of this P-wave shape resonance. And that is important, needs to be taken into account whenever you talk about high-density experiments and dephasing of whatever sort, also in another context. The line shape is not trivial. So what happens at this resonance is shown here. So this is actually a happy S electron. Yes, it's a Dalgarnian shells of nodes and antinodes of the wave function if you take a cut through such an S state. That's if the ground state atom is sitting way out here, away from this resonance. This wave function is actually not perturbed dramatically. Yes? The binding energies are much, much smaller than the distance to the next Rydberg manifold, so you can safely neglect the back action of the ground state atom on the electron wave function. However, when you are sitting close to this resonance that is shown here, at this particular distance, this is now where the ground state atom sits, it does resonant P-wave scattering, and it totally alters the Rydberg state, and these guys were named butterfly molecules because of the P-wave symmetry, basically, of the underlying scattering physics. Okay, so now that is sort of trying to understand the line shape, assuming that nothing moves. But also in the spirit of Alex Dalgarno, I thought we should also talk about a little bit of chemistry. Let's say, let's let the atoms move and do something inelastic, or just change their state. And the situation that we have here is actually pretty interesting, yeah? Because we are working with very cold atoms. They are so cold that even by the excitation of the laser, if they are sitting inside this potential, that's again the internuclear distance. This time we use just S-wave scattering for the 40S state. That's the blue potential now here. Here is the outermost lobe where you would see this dimer bound state. Then you see that if you have atoms inside here, you excite them, let's say with 100 kilohertz tuning in this case, they will not be able to escape. They are bound. This is a bound system. This electron binds all the atoms inside to its orbital. Okay. And so what they can do is they can fall inwards. They cannot escape outwards, but they can fall inwards. And then the question is, what happens with the electronic state? And can there be an inelastic process? And indeed, there can be inelastic processes. For example, let's look at this graph here that was provided to us by Jesus Perez-Rios and Chris Green. This is the potential landscape of a ground state atom sitting in a Rydberg orbital. This is a logarithmic scale of the internuclear distance here. And let's say we start in an S state, 53 S state again. So that is how the electron wave function actually looks like. In this case, it's cylindrical coordinates with some 0 here. Then what if the atom starts to move inwards, because it's attracted to the inward direction? You see that if it sits here, it gets attracted to the inwards to shorter distances. Then eventually it will hit a crossing, or an avoided crossing, with some lines that come from above here. And this is exactly this P-wave shape resonance point. There's an avoided crossing such that the dynamics will always be adiabatic and the particle will roll down this hill very quickly. So here now we are talking about gigahertz of energies, tens of gigahertz of energy. This is basically given, this scale is given by the Kepler frequency. Yes? So here we are talking about neighboring 52S, 53S neighboring manifolds. Okay. So quickly the atom can gain a lot of energy, go inside, and eventually even change its state and come out at a completely different Rydberg state. So on a very fast time scale in such a collision, what can happen is that the electronic state is totally changed, and this energy is then given to the ground state atom, and of course the Rydberg atom. They fly apart as a result of this exothermic reaction. Can we measure this? And the answer is yes, we can measure this. So if we prepare a Rydberg state and the ground state, we let the reaction happen. It happens on a time scale of microseconds. We change the L and maybe even the N by this reaction. And what we can measure then is what is the energy that is released to the Rydberg atom. Because what will happen is that initially we have very cold partners, but then they gain energy and they fly apart. And we just measure this kinetic energy by a time of flight method, essentially. Yes? So if they fly apart and we extract these ions after field ionization to our MCP, what we see that as a function of arrival time, we see a broadening, basically. Yes? And this broadening essentially reflects the energy that is provided in this chemical reaction. So there's some way we can analyze this data in order to extract the released energy as a function of principal quantum number. And you can then see that if you do this for different principal quantum numbers, that the measured energies are good evidence for state changes just between neighboring levels. For example, from this 53S to the 51D, which is the neighboring level, that would correspond to this line here. If it goes to the P, then it's the yellow line. And if it goes to the lower hydrogen-like manifold, then it would correspond to this red line. And our measurement points, let's say, would indicate that maybe we come out here or here. That's in the, we have an L change in collision, but sort of we are not going all the way down to much lower states. Okay. And this is so for principal quantum numbers between 50 and 150, so it's over a very wide range. You can also confirm that there are L-changing collisions by just looking at the field ionization behavior. If you do this excitation, you let a chemical reaction happen, and then basically you measure with the field ionization ramp, where you constantly increase the field strength, like in a traditional field ionization experiment. Then you see that at short times, you ionize at lower fields, which means that the L is a small number, whereas at larger times, so you go all the way out to 50 microseconds, the field ionization field has maybe doubled. And that can be explained that if you start with an S state, the electron sort of experiences the Coulomb potential at twice the distance, or than the, let's say, circular state, and therefore you need more field, twice the field to field ionize. That's not, yeah. At least you need twice the field to field ionize. Okay, with this kind of measurements, you can also characterize all the time scales for these L-changing collisions as function of principal quantum number, and there you see something interesting. This is a logarithmic plot. Yeah, this is 1 microsecond, 10 microsecond, and this is the principal quantum number. if you do, let's say, Monte Carlo simulations, let's say of classical type, you can explain this kind of behavior here. The time scale for the classical dynamics is more or less 1 microsecond. But what cannot be explained, and we still don't understand fully what is happening, is this sort of threshold behavior that we observe at around principal quantum numbers of 100. Above 100, it seems that these ground state atoms are sort of hindered to do this chemistry, and they need several attempts, basically, until they eventually do this inelastic process. So here, basically, everything is consistent with if they get accelerated, come close, then there will be such a chemical reaction and they could fly apart. But above 100, these timescales actually increase by at least 1 order of magnitude, and there is a mechanism that prevents either the particles to move together to do this chemistry, or prevents the chemistry at short distances to happen at all. So candidates for this is maybe quantum reflection, you know, from these periodic potentials, but theoretical understanding is still lacking. But this is very interesting, because it means we have very long lifetimes for high principal quantum numbers, and that's what we actually want to have. I can skip that. Well, okay, no, it's Alex Dalgarno lecture, so I should have one more slide on some chemistry. There's another channel actually. Every once in a while we see that we not only see fast Rydberg atoms coming out of this reaction zone, we also see Rydberg rubidium dimer ions coming out. So deeply bound rubidium dimers with a positive charge. We can separate them in time of flight in our detector. Yes. They have twice the mass, so they arrive spherically 2 times later. So in order to understand the physics behind this, you consider again our 53s atom here, and then sort of the idea is that by some mechanism a deeply bound rubidium dimer is formed, and this binding energy is enough to kick off the electron, such that we don't need to do the field ionization. Now we can observe these rubidium-2 class molecules here, and we compare the signal of atoms to dimers, and we see that at low principal quantum number it's about 50-50. Yeah? 50% of the time we get a state change of the single Rydberg atom, the other half we get the formation of these dimers. But if we increase the principal quantum number, again around 100, this signal of the dimers goes totally away. And in this is a pretty busy plot. You see a lot of data at vastly different densities, like 10 to the 12, 2 times 10 to the 14, 2 microkelvin. D-state data, S-state data, doesn't matter. This ratio is sort of universal, and it's by now also confirmed. These black dots are the theory by Chris Green and Jesus Perez-Rios. So this dimer formation is something that happens only at low principal quantum numbers, and it has to do with the avoided crossings in this potential landscape that I showed you earlier. Okay, and a timescale for rubidium-2 formation is also on the order of 1 microsecond, but again, at around 100, this process stops. And we have no rubidium dimers anymore. And that's good, because now we want to use high principal quantum numbers in the condensate. Okay. So let's talk about principal quantum numbers 100 to 200. So those guys live long, and they can sort of interact with the condensate and its collective modes more efficiently. So just to get the order of magnitude, if you have a 110, I remind you, the radius is actually 1.2 micrometers. That's this blue sphere inside our condensate. That's actually the shape of our condensate. It's a cigar. If we blow up the principal quantum number to 200, then the Rydberg atom is as large as the condensate. In this experiment, we choose a particularly large condensate that reacts at relatively low density. So this is about 80,000 atoms in the total condensate, but this red Rydberg orbital contains 30,000 of those. Okay, so now we talk not only about 1, 2, 3, 4 atoms inside the orbital, but tens of thousands of atoms inside. Okay, let's see what happens. So the first thing that you can do is you do spectroscopy. You just ask, as a function of frequency, how many atoms are left behind in my condensate. And you see for the low principal quantum number, well, there is a line. Once you hit the Rydberg resonance, there's an interaction with the condensate. It somehow kicks out some atoms out of the condensate. You see a loss, in this case, of 30% of the atoms. You see that the maximum of this loss is not at 0, it's actually shifted. That's the Amaldi-Segre shift. You all understand this by now. That's the density that we have here. So the shift is about 10 megahertz here. And there's a broadening. Yeah, so that's, you would think, okay, physics of the 30s, shift and broadening. Okay. Then you increase the principal quantum number to 200. Now, physics of the 30s will tell you that should be the same shift. It should be the same broadening. Now you see, that shift is slightly different. It turns out to be a finite size effect in the end. But what is more puzzling is that the coupling to the condensate is much weaker now. Yes? Remember, every time we do it, we excite a single atom. So somehow the coupling of a very dilute electron to the condensate is weaker than the coupling of a more focused electron orbital, a smaller orbital. Okay. So, and that's counterintuitive. Yeah, in the small guy, in the small orbital, you find 700 atoms, and this measurement tells you that about 50 atoms of those are kicked out. Whereas for the big one, you have 30,000 atoms inside, and only 7 are kicked out. And that needs to be understood. We have to find some way to explain this. Another observation is the following. If you just look at the condensate itself, after you put a Rydberg atom inside, then you look at, for example, the radius in the z direction, you see that the whole condensate starts to oscillate. It has a collective oscillation, so that's a quadrupole oscillation. And you can measure this amplitude of this quadrupole oscillation. That's also sort of a measure of the coupling strength of this electron to the condensate as a whole. Okay. This is just a background telling you that if you don't have Rydberg atom, nothing happens. It's basically detuned excitation just to make sure that this is not done by the light. So we can have another plot like this where we plot the amplitude of this quadrupole oscillation as a function of frequency, and we again see that if we have a very small Rydberg orbital, we couple strongly, this amplitude is big. It's also shifted, of course, by this Amaldi-Segre shift. But if we go to the very large Rydberg orbital, 200 US state, condensate doesn't care, it doesn't oscillate. Okay. So we did all these measurements for all, not for all, but many intermediate principal quantum numbers. And it's just a systematic trend. Yeah? So if you go from 110 to 125, 140, 160, 180 to 200, there's a gradual behavior with the size of this orbital. And the same is true here, actually, in this part. Okay, so how can we understand this? Well, let's look at a simulation that was, in this case, done by Karli Krzyzewski and his co-workers. That's a Gross-Bidayevsky simulation, where you put a single Rydberg atom in the center, and now you have this interaction with this pseudo-potential. Oops, that's already over. Okay, let's look at it again. Oh, like this. Yeah. So you see that you put the Rydberg atom here, and what happens is that the superfluid basically flows into this attractive potential. Eventually, you can actually see the shape of the Rydberg atom in the cloud, and we will come back to that. Now, what happens is you are exciting phonons, and you are also exciting free particles that eventually couple to the collective motion of the whole condensate, and also lead to losses if you do it many times. So without going further into the detail, if you take this kind of numerical approach, that's these red points, and you ask how many atoms as function of principal quantum number get lost for our parameters, then you see this can very nicely explain our experimental finding. There's an alternative method that is not numerical, just based on Gogol-Lyubov theory of excitations. There you have to distinguish between the sort of collective phonon modes and free particles. And you basically see that the form factor of the low frequency or low momentum excitations is suppressed. And that is basically the reason why the big orbital, which mostly couples to low momenta, has a much suppressed coupling than as compared to the small orbital. Okay. And this kind of theory, that's the triangles here, also more or less give the right behavior for the losses in our condensate. Okay, so to summarize this, I've shown you that basically the Rydberg orbital is first of all trapped by its core. So the ion at this point was just serving as an origin of the Coulomb potential trapping the electron. We use a Rydberg blockade to single out a single excitation, and then we have a light electron that interacts as a single charge with the condensate, and it can interact with up to several 10,000 atoms at the same time in this wave function. And we can see and understand the coupling of this single electron impurity with the connecting BEC excitation modes. So I have a nice movie here, so I have to show this. And now we just increase the principal quantum number, and that means the size of the Rydberg. And this is the condensate, this whole blue cloud here, and eventually it's as big as the whole condensate. So what can you do with this? Let's look at this idea. That's actually the outlook of my talk, so that's what we are working on. You have seen in this little simulation that the superfluid condensate actually wants to flow into this orbital. So why not use this as an imaging technique for imaging electron orbitals? If you remember your chemistry lecture, you have seen orbitals. Yes, they are P-wave orbitals or B-wave orbitals. But if you ask yourself whether you have really seen one with your eye in some experiment, then at least I have not seen a direct measurement of the shape of an orbital so far. And so I always believe the chemists, of course, that it looks like this. But that's enough motivation for me to develop an imaging technique that would allow us to detect the orbital of a single electron due to the interaction with tens of thousands of ground-state atoms that I can later on image. So these are orbitals. Of course, I should be precise, we will not be able to see the radial part of the wave function. What we are aiming at is just look at the angular part. But remember, our principal quantum numbers are 100 or larger, so the size of this orbital is several micrometers. So with an optical microscope, you should be able to resolve this. Okay, so if I take, let's say, 140S, I smooth it with my finite resolution, 1 micrometer, let's say, in our microscope objective, and I do the line of sight integral, I can clearly distinguish those three orbitals just by a direct, let's say, absorption image of such structures. Then you can ask, well, does it really work? And that you can check with the numerical simulation. This is again a condensate, a very elongated condensate across the whole room, basically. This is a radial direction. And now if I let the simulation run with one of these orbitals inside, you see that after some interaction time, actually 150 microseconds or so, if you take a picture at this moment, yeah, you get a nice idea at least of how this orbital must have looked like. Good, so this is conclusion and outlook. This is what we are working on. The key ingredient for this wave function imaging technique is that the lifetime of Rydberg atoms is long enough such that it interacts long enough with the condensate. So the movie that you have seen was about 10 microseconds interaction time. Then something bad happened, some chemistry happened maybe. So that is fine. Actually, it's all based on this threshold behavior that we don't really understand. Yeah, but we you see that we have these long lifetimes, 10 microseconds. And then the only thing that we need is a very sensitive, high-resolution absorption imaging. And of course, we have to work with very high principal quantum numbers, sort of control our electrical fields well enough such that we have stable conditions every time we do this. This is exactly what we are working on. Okay, with this, I would like to thank my team. Here you see the team of PhD students. Michael has finished, Carl has finished, Katrin is now the leading PhD student in the lab. Fabian has actually finished his master thesis. Here you see also Tara Bubliebe, she did a postdoc with us, also finished by now. Sebastian Hofferbert, some of you might remember him, he's a very important team member here as well. And here is Chris Green and his postdoc Jesus, where we have collaborated on the chemistry part mostly, which was very crucial for us, for our understanding what is actually happening in these universities. Okay, so thanks a lot for your attention.
Questions, John?
I'm sure you've already thought of this, but the low quantum numbers, are you just getting kind of peakier densities? The atoms are coming in and they're forming a higher local density, and that's why you're getting the more rapid loss, as opposed to the larger atom, which.
Okay. So if you do this simulation, it's all happening on a microsecond time scale. So there's only one atom at a time that is coming very close to the nucleus and is very fast. Yeah. So once it is basically rolling down this hill, everything happens in 10 nanoseconds or something like this. Yes? So there is no phase. I mean, you might have the picture that all of the atoms at the same time basically meet and then do all together do some chemistry.
Or at least
high density. Yeah. But this is not the case. Our potential landscape looks like I've shown in this one potential picture. Like here, where was it? Here, this one. So atoms more or less live happily on this plateau, and then if it comes very close to here, then poof, it sort of goes very fast, and comes back up. Okay? And that's always
there's no
one atom at a time.
No many-body at all. Okay.
There is a many-body. Okay, so if you ask about many-body effects, then you have to ask what happens if this guy sits exactly here, yes? Or if it moves through here. That's actually an interesting question, because at this point we hit this p-wave shape resonance and our electron orbitals change. And then of course all the other guys that were living in this flat potential over here suddenly see a very much different electron density. And these many-body effects are actually not taken into account in any of our calculations so far.
So why you're never talking about the interaction of positively charged ions?
Yes,
Yeah.
very good. Yeah, I promised this actually, so now I have to answer.
And we know there's also interactions.
Yes, there is interaction. So, first of all, the length scale of interaction with a heavy charge goes like the square root of the mass. So, already in this Fermi derivative, let's go very back here. Here I have this on my transparency here. Yeah, this mu, basically. This means you would say, okay, my ion has a much larger length scale here. Yes? But the interaction energy itself goes like scattering length divided by the reduced mass. So the overall effect of the electron in terms of interaction energy is actually square root of reduced mass ratio larger than the effect of the ion. So the mass ratio is 100,000. Square root of this is maybe 300. So the effect of the electron is 300 times stronger than of the ion. If we would measure with the precision that would resolve, let's say, on this level, then we would also see the effect of the ion. But this is not what we do.
Do you believe the ion causes no loss?
Well, of course, these short-range potentials are heavily influenced by the presence of the ion, and there is a part of this potential is a 1/r4 potential, which is caused by the ion, of course. Yeah? So if you come to very short distance, then the ion is important. Without the ion, you can't understand the potentials, like here. Yes? So, I mean, the 1 over R4 potential kicks in here at very short distance.
I was wondering, you didn't realize that the delta function
Yes.
potential is not correct, it doesn't have the correct short-range boundary conditions. You never seem to worry about that here, probably because you don't
Yes.
care about the short range, is that right?
Because of the variation of the wave function on the scale of the length scale of the interaction on this 18 Bohr radii is smooth, basically, and we don't have to worry about this correction. At the moment, when we have very fast ripples here, you know, at the inner part, yeah, then it becomes different. Then it becomes important.
Would you expect that you really couple to the collective modes if you have 10 microseconds lifetime, that's about 100 kilohertz,
Yes.
and the healing length, so you have 100 not a Speckmann scattering length, which would give you probably kilohertz.
Yes, very good question. So I'll show you this movie again. Yeah? You see, over the first 10 microseconds, nothing happens. Yeah? Only after 50 or 100 microseconds, stuff seems to develop. Okay. So in that sense, our Rydberg atom in former times, we call this the Raman-Nath approximation. Yeah? So when you imprint a potential for a very short time, what it does is a phase imprint. And only on much longer time scales, this phase imprint actually converts into a density modulation. This is our case. This is exactly what happens. Go ahead.
So with this imaging,
Yes?
so I wonder, don't you want to actually try to image this entire structure, including kind of observations?
Sure.
Because otherwise, everyone shows these pictures. I mean, are they really real, or is it just
Sure. Ideally, you would like to resolve also the radial part. Unfortunately, we just have an optical detection technique, and that cannot resolve it.
Actually, I kind of wonder why, for example, if you have, for instance, if you have these atoms that are taking middle traps, you can for sure try to basically just...
Yes, if you have a means to position your atoms, let's say in a lattice or so, much better than the wavelength, then in principle you can get more information.
And this resolution that you need is 100 nanometers. It's not...
No, it's not crazy. So for us, at the moment, it's just... But, okay. I still think that the angular part is sort of the real interesting part. I mean, think about a movie. So what we would be able to do is, let's say you take an S state, write a microwave to a P state, and you start to see the... And the interesting part is the angular part. So you do a movie of what you have in your lecture, S to P and back to S.
But it does not really, kind of...
It's not
kind of
complete.
It's not, does not show data.
Ah, okay, so the animals, yeah, of course, you will have to smooth over some parts of the animals. Yes, yes, yes. And, yes. But it's not only a spherical tower that is in some structure.
Okay, that was just too good a final word. The spherical cow. Let's thank Tilman for what